forget to do. If life gets busy and you did not get a chance to complete the quiz, go ahead and do that by the end of tonight. It does look like we have a few people that were missing today. We have 2 missing students. So hopefully by the time they see this, they get to complete the quiz. All right. Any specific questions? Are we good to move on right ahead?
Are you, like, do you mean questions about the quiz?
Well, yes, but questions in general are allowed also.
I mean, we're probably not going over the quiz just yet, given that we just took it, so never mind.
Okay. Was there something specific that you're curious about?
Yeah, it was just one of the questions. I think I may have had a little bit. It wasn't like a hard question to interpret. I think I was just thinking into it a little too much and wanted to ensure that I was on the right thought process, if that makes sense.
So I will say most often when students are like, oh, that was a really hard question, it's because they did exactly that. They thought a little bit too much. Again, my style, and you guys are just getting to know me. So this is a learning process for everyone. I am not tricky. I'm pretty straightforward. So what's out there is probably what it means. Similarly, if on a quiz or a test, you guys have responded and I'm like, I think they know the answer. This is not fully it. I may just go back and ask you and give you an opportunity to clarify. Again, this is a semester of grace. This is a weird environment. We are all signed up for something we probably originally weren't signed up for. This was going to be in person, far more interactive. We're going to do SPSS, but again, with the size classroom that I was given, the number of you, safety wise, it just doesn't make any sense. This is a better setup for that, but all to say it's a normal learning curve. So absolutely. Okay, how did it go last week for you guys watching the video? Did I talk fast? Was it crazy or it was okay? Okay. So okay. So per the requirements, as I described, thank you for the thumbs up, letting me know. The goal was to have you guys also create your own original post. And I think the discussion thread was on there. Let's see, where was the thread? The stats discussion is what it was called. So make sure you go and click that. It's really by the end of today. So when I look at it now, it looks like the bulk of you, 2, 4, 6, 8, 10, 12, 13 of you responded and created your own individual thread, but it was a 2-parter, right? So it was per the instruction, it was create your own post and then comment on at least 2 classmates' post. So to get full credit for that, you need to go through, and several of you have done that already. But if you have not had an opportunity to respond to 2 classmates' threads, why is this so hard to say? Provide 2 responses. Maybe that's faster. Or more. Obviously, you could do more. Make sure you have an opportunity to go and do that because there's a few people who have had no responses to their post. So it'd be nice to get a response. Really fun topics that you guys came up with some hypotheses. So that was cool. So make sure you complete that and that'll go towards your participation scores for the class. Okay. The goal for today is we're going to go over lecture. We're going to talk about how we organize data. And then next week, I'm going to introduce the lab, and the lab will be due that subsequent time as well. So we're going to go over that discussion next week. Okay, so let me share my screen, make sure that everybody can see. And this is lecture 2, if you look on Course Connect. Make sure I can swap that. Okay, can everybody see the lecture? And I am recording, right? Yes, okay. All right, so the reason why we do this in statistics is if we just talk about math, it usually flies about 6 feet above people's heads. They're like, what did you just say? But if you're able to show them a table or even better, a graph, people are able to grasp statistics far more simply. So it is a huge aspect of what we need to learn. So we'll talk about how to construct and analyze a frequency, percentage, and cumulative distribution. We're going to talk about proportions and percentages. We're going to compare frequency and percentages distributions for nominal, ordinal, and interval ratio variables. And we'll talk about how to construct and interpret charts and graphs. So that is our big goal for today. All right. Several of these examples are straight from your text, so some of them can be a little wonky. That's just how it is. So let's talk about frequency distribution. So it is a list, a table, or a graph that reports the number of observations that fall into each category. So this would be an example of that. This is the frequency distribution for categories of region of birth for foreign-born population in 2012. So what they did is they asked, this is according to the census, as you can see right here. Now, quick question, census, is that a sample or a population?
Population?
Population, yes, you are getting every single person's response, right? So a census is an entire population. So the census from 2012, they looked and asked the question, were you born in the US? Yes, no. If no, where were you born, right? And they tabulated those responses and they were able to see that Mexico was number one in terms of the highest number of foreign nationals that lived in the US that were born in another country. And you can see here 11 million and change. And then down into South and East Asia, which I get a little annoyed with. What's wrong with this distribution here? Maybe this is just a pet peeve of mine. Maybe I need to own it. We have a country and then we have regions and a continent. That seems odd to me. I guess you could say what is the most frequent area and then Mexico would fall into it. Anyway, okay, so you can see here different distribution. This is a way that we can classify data. We have counted the number of individuals that came from each of these regions and put it in a table. So when you see a frequency here, these are single counts. It's not cumulative. There's been no addition, multiplication, nothing like that. It's just a literal count of how many people were in there. It is the most basic way of organizing data, and it's usually the first step in data analysis. And in fact, this is something that my kids, even in first and second grade, they start to organize data this way. And it's usually through like tally, right? They'll ask students, go home and figure out how many in your family, like chocolate ice cream. So chocolate, you do these dash. Okay, so this is the 4 people. How many people like vanilla? And then you've got these dashes, right? And then from there on, you can write here, this is 4 and this is 5. Right? So you can see this is the frequency and these are the tally marks. Hopefully this is not brand new information. Everyone's like, yep, I got it. Frequency table, I got you. I know how to count. Now a proportion falls a little bit differently. It's a relative frequency obtained by dividing the frequency in each category by the total number of cases. So when you look at the proportion, the total should always sum 1. But it's going to be the number. So in this instance here, let me get my little, whoops, where'd it go? Here. So it would be like this 11,489,387. It would be that frequency out of the total N, which is 40,738,224. That would give me the proportion of individuals that come from Mexico. Again, this should not be earth-shattering. This is something that we do quite frequently. Now, if I want to have the relative frequency, I can also look at it as a percentage. So it is doing the same thing. I'm getting the proportion, but then I'm doing the proportion times 100, and that will give me a percentage. Okay, so this is a table that shows the percentage of observation that falls into each category. So this is a frequency distribution of the number of children in a household. So again, this is the General Social Science Survey. It's a subsample. The number of people who said they had 0 children was 13. Those who had 1 child was 9, 2 was 6, and so on and so forth. So you see the total N is 40. So if I'm looking for the proportion of each of these, so let's say the proportion that had 13 that had zero, come on, thing. Proportion of people who had no children, I would do 13, that's a 3, there we go, divided by 40, right? And that would give me 0.325. Okay, and then I get this percentage by doing times 100, I get 32.5%. Okay, so as you go through these calculations, you're able to create a table that exemplifies the number seen for each category. And then I can also do a percentage for each. Make sense so far? Good? Okay. If there's any questions, please stop me because I can only see, the lecture class. So if no one is telling me, hey, I'm totally lost, like if you just do this, I'm not going to be able to know. So you gotta speak up. All right. This goes back to something I just said. So oftentimes with nominal variables, you can just do tallies and then you end up with a frequency. So in a classroom, I may be interested to see what's the distribution between males and females. I would do then tally marks. This is a weird example from your textbook because we usually do tally marks with like a bunch of 4 and then 1 across as your 5th. Anyway, this is much harder to see. But then you could write what is the actual frequency from it and come up with a percentage. Now, remember, again, the total percentage always has to be up to 100, adding up all of your categories. Okay. Similarly, you can do a frequency distribution for ordinal variables. So the one right before that was a nominal variable, whether you're male or female, you could do the same thing for a political party, right? Like that's a nominal variable. With an ordinal variable, you're rank ordering it, like you probably saw in the quiz today. So what is the responses from people that took a questionnaire as to how they rated their level of happiness? So there's 3 levels: very happy, pretty happy, not too happy. And then where does that fall? And you see that 62% falls in that pretty happy category. You usually end up ranking these from ascending or descending order. You're gonna order them based on the levels of your variable, not based on the percentages you get, right? So you're gonna either go from low to high or high to low, and then report the percentages and frequencies from there on. Okay, so this is another example of how we can use a frequency table. This is the total number of social interactions over the course of 1 week. So this particular researcher, McLaughlin and Volpe, in 2001, your text has a whole discussion about this particular study, but they asked individuals, how often did you have a social interaction during the course of your week? And they operationalized a social interaction as having a meaningful interaction face-to-face with someone else. This is back in the good old days of 2001 when you saw people face-to-face and not via Zoom. And then they had them mark how many times over the course of the week they had a social interaction, and now they displayed their score. Now, how do you guys feel about this representation? Like, is this clear? Does it feel easy to see? What are your thoughts? Annette, I liked your face. You were like, that's kind of how I feel about it. Anybody else?
It doesn't seem realistic. I don't know, unless people just don't go out of their house.
That's true. Right. Well, and again, we would have to go back to that original source, that original study, and see how they defined a social interaction. It might have been like a really meaningful social interaction, so people were more likely to minimize. But if someone is asking you like to interpret this table, how easy is that to interpret? Or is it kind of complicated?
I feel like it doesn't give, I mean, looking at the table itself, I would say if like the little sentence above it is equated to the title, then I would say it's not too hard because it kind of tells you, but I think the table itself doesn't really give much information besides, just some numbers and tallies. So But besides that, I would say it's not too hard to like, I guess analyze the data that it does give.
I would say this is, so I hear what you're saying, Hasher, you're totally right. When you read the title, you're kind of able to figure out, okay, this is what it means. But to be able to quickly look, and again, that's the whole reason why we organize and display data, right? Is to convey a more complex statistical message in a quick visual way. This is not doing it. And the reason why is there's 48 entries. So if someone asked you, do most people have more than 20 interactions a day? You would have to go through and go, well, I don't know. Eyeballing it, yes, no, I don't know, right? Like this is a bad table. It is not conveying the message that it is trying to do. We need to simplify that. So, okay, one way to simplify it is by writing it out in numbers, right? So already this is a little clearer than this, right? I would still say this is not super clear. Whenever you have a table that is going to span 3 rows, that's no bueno. We don't want that. This is much better. So what has happened here is we have taken our entire data and we have created groups so that we can look at different different literal groups that are the same interval to then compare the different frequencies. This here provides a lot more rich data. You can take a peek at it and go, oh, okay, yeah, I am seeing a trend. I'm seeing that really after 30 interactions or after 29 interactions, it really drops off significantly. It's not really that meaningful. Most people have up to 29. In fact, most people hang around this group here between 5 and 19 interactions per week. So you're able to glean information far faster once you group. So groups are then called class intervals. And you get a number of class intervals, and the width of each class interval is really up to the researcher. So if I wanted to, I could look at this table and go, you know what? I just want easy numbers. I want to go 0 to 10, 10 to 20, 20 to 30, 30 to 40, and 41 and higher. I could do that if I wanted to. But you need to have some sort of rationale as to why you're grouping things in a certain way, right? It needs to tell a story. So you want to make sure that your class interval is large enough to avoid too many categories. That's our goal again. We want to try to simplify and condense the data, but that it's small enough not to obscure significant differences between categories. So for instance, you don't want to go 0 to 30, 30 and higher. That would be too simplistic. We would lose some of the nuances in the data. Okay, does that make sense? Okay. All right. Again, this is a grouped frequency distribution of variable age. So again, I could have had one entry for each age group. How many are 20? How many are 21? How many are 22? And so on and so forth. That gets out of control real fast. So you need to find a meaningful age category, and a 10-year span or so that's commonplace, kind of a gold standard. I will say, have you guys filled out those surveys before where they ask you which age group you're in? And all of a sudden you're like, wait, what? You're putting me in a group of people that I don't think I belong to. That happened to me for the first time. I think I was, I had turned 35. So I'm 39 now. I was 35 and the groups were like 18 to 22, 23 to 29, 31 to 34, 35 and above. And I was like, you are lumping me with people who could be 80 years old. How are we in the same group, right? So be kind to your participants. Don't do that because that'll hurt their feelings. This is an appropriate age band, right? You're looking at a 10-year age band. That's far more common. And then you can see the frequency here for each age band and then the percentage that it represents. So this is how you'd want to divide that up. Again, far more easier to read, quicker to take a look, see what is popping up in your data. You can visually see it rather than an entry for each age. Okay. So these are stated limits versus real limits. What we can see is depending on the percentage. So you've got, let me take a step back. This is the same table we looked at before, right? So we've got each class or age band, and the frequency within each. Within that, you can look at the real limits. So that means if some weirdo said, no, I'm not 29, I'm 29 and a half. No one does that as an adult. If you do, please explain to me why you do that. I feel like only like a 10-year-old would do that. Like, no, I'm not 10, I'm 10 and a half, right? Or a 3-year-old, I'm 3 3/4, right? The stated limits is what we are presenting to our participants to kind of as a forced choice. How old are you, right? It goes in there. The real limits include kind of a buffer zone, right, on either side. So you've got kind of a space of error. Again, with age, that's not really a thing, but if you were to get height, right, you would need to know where to put somebody in which category. So you get kind of half a point on either end as the real limit. And you can note your midpoint on there. That's just, again, more data for you to consider. All right, when you're looking at a cumulative distribution, what do we hear? When you hear cumulative, what does that mean to you? What do we think cumulative means?
Like total?
Total, right? Usually students tell me, is the final exam going to be cumulative? That's usually the context that we use the word cumulative, meaning cover everything and before, right? So remember that. If you're asking, is it going to be cumulative exam, is that you're going to go all the way up at the front, at the beginning. So that's exactly it. A cumulative frequency distribution, it shows that frequency at or below each category. So every time you have a category, you are adding the one above it, okay? Similarly, a cumulative percentage distribution does exactly the same thing, but for a percentage. So let me show you what that looks like. So this is the frequency. We've looked at this table a few times now. So this is the frequency in each age band, but the cumulative frequency here adds the layer above. So I've gotten to 14 here because I'm doing 7 plus 7 equals 14. Now 14 plus 12 equals 26. 26 plus 3 equals 29, and so on and so forth. So you are adding up the categories above it that came before. And then for percentages, the exact same thing occurs. So you're getting each of these percentages for each of the bands, and the cumulative percentage, you're adding the one below. So 17.5 plus 17.5 equals 35. 35 plus 30 equals 65. 65 plus 7.5, and so on and so forth. Okay. So that is how we look at cumulative percentages. So on both ends, it's just adding whatever came before it, so that you total up to 100 at the end. Okay. Rate. The rate is a number that is obtained by dividing the number of actual occurrences, that's your frequency, in a given period of time by the number of possible occurrences. So the total N, or the population of thereon. So that could be birth rate, that could be unemployment rate, marriage rate, poverty rate. Notice that when you're saying, how do I calculate a rate? The title usually is in it. Oh my gosh, Annette, I love your puppy. Is that a golden retriever? We have a golden retriever who's upstairs now because he's been wild. I've been teaching all day and he was outside earlier next to me and he was barking at me to put him out. There were deer, he chased them, came back in, then he's like, rah, rah, rah. There was a squirrel. I was like, oh, I can't have you downstairs while I'm teaching. But yours seems very docile and kind and sweet.
Most of the time.
How old is he older or?
He's 5 and a half.
5 and a half, right? You have a golden too, Mallory. Wait, is there a picture? Is your golden with you? Now I feel like I need to go get our little Oakley Moakley is what we call him, but he's not even 6 months and he's giant. He's like at that awkward, I've got big paws and like gangly teenage age. Okay, I made a sharp right turn here. I was talking about rates. Note that whenever you're calculating a rate, usually the name's in the title. So birth rate, marriage rate, divorce rate, poverty rate, all of those. If there's a rate in it, that's how you're going to calculate it. It's going to be by taking the number of frequency divided by the population at large. Okay, so how would we go about doing that? Sorry, I'm on the struggle bus here. There we go. Trying to get your faces out of the way and it's not working. There we go. All right, so I could look at the US Census Bureau for 2014. So to calculate the poverty rate, if I'm wondering about the poverty rate, poverty rate in 2014, I would take the total number of men and women that are in poverty in 2014. First off, by the way, I need to figure out what is poverty. We'll talk about that in a second. And that would be divided by the total population in 2014. So that's the actual occurrence divided by the possible occurrence. So the poverty rate, and again, it was counted, I think, by 20, I think I have it written somewhere here. Let's say it was like $21,000 per year was the poverty rate, right around there. So 46 million people qualified based on that definition of poverty out of 315 million people, again in 2014, which comes up with the 15% poverty rate. Now I can actually dive deeper into that. Now I can say, well, what's the poverty rate for people that are 18 years or younger? So then I am taking the total, population in 2014 that were poor, but I'm, really titrating down to 18 years and younger. And what we found was it's 15,540,000. But then I don't divide that by the total population of 2014. That wouldn't be an accurate, representation of the rate. What I divided by is by the total population that was 18 years old and younger. So note that this number is smaller. So that's 73 million. But then my poverty rate is at 21%. So that's even higher. So rates are often expressed as rates per thousand or 100,000 to eliminate all of those decimal points. So it makes it a little easier to understand. So oftentimes they'll say, 150 people in 1,000 people are poor, rather than saying 21% or 0.21. So again, you're taking the actual occurrence that fits what you're measuring against the possible occurrence of what you are measuring. Hopefully that's making sense. Okay. Okay. I think we can skip that because I guess we can talk about this real quick. So if we looked at this table, that's part of what we need to understand too, is where do we get this information and what is the information about? So this table is kind of crummy. So here's our questions. Let's remind ourselves. Where did we get this table? How many variables are presented and what are their names? And what is represented by the first column of numbers, second column, and so on and so forth. All right, so what do we think? If you're looking at this table, what are we looking at? What's the information? Someone give it a shot. And then tell me how we could improve this table. All right, so first question, what is the study? Where did this data come from? What's the name of the study?
The Child Wellbeing Study?
Yes, so right here, good job, Aaron. It's the Fragile Families and Child Wellbeing Study. That is the title of the study that this data is coming from. Now, what are they showing us? What is it they're trying to just show to us or display to us or, yeah, I'm using the same words because I'm trying not to give it away. Okay, maybe let's take a step back. What are they trying to compare? Which two groups are they comparing?
Mexican born versus United States.
Yes. Okay. So not just whether you're Mexican born or just United States, it's unmarried mothers. So like we're titrating it down, right? So unmarried mothers, whether they are Mexican immigrants are US born, but both of them are unmarried mothers. Okay, so that's the group we are looking at. Okay, and how did you know that, Hasher?
Just looking at the titles, I mean the title of the chart or graph or whatever it
Up here?
yep, right up there, and then I don't know if it's always the same, but isn't like one always kind of the x-axis or y-axis or whatever, and they kind of stand for different variables?
Yeah, so oftentimes, you're absolutely right. Oftentimes your title will kind of exemplify which variables you'll at least be looking at in either a table or a graph. Yes. And specifically with this one, you see this big division. So right up here, you've got Mexican born, and here you have US born. But then it's subdivided even more. So let's talk about that. How are they then comparing US born? Do they just leave it as a clump, or is it subdivided?
Subdivided.
Yes. In what way did they subdivide it?
By race.
Yeah.
Kinda? Okay.
So, but kind of a funky division. So they have Mexican American, they have Black, non-Hispanic, white, non-Hispanic, and then the total US born population. Okay. So this is your comparative group. They've really divided these three to compare to the Mexican immigrant. That's, I think, their goal. Okay. And then what are some of the variables they are measuring with this table?
I see that. Oh, sorry. I see that they're measuring like health insurance,
Yeah.
like food stamps, rent assistance.
Any government funded assistance?
Yep. Okay. So again, there, and then there's a couple people piping up here. Yep, Grace, you got it. So whether they have, any sort of federal help, like Annette mentioned. So you see here in this category, did they have health insurance, right? And what type? So that's broken down between Medicaid, private insurance, or other. And then you have here a slew of assistance, federally supported assistance that's provided. That this TANF, it's temporary assistance for needy families. And then you can see through here at the very top, it tells us percentage, right? So then I know all the numbers I'm looking at are going to be percentages. So out of that group, how many then received Medicaid? So of those who were Mexican born, 77% of unmarried mothers received Medicaid. If I go through here, 70% of US born white, non-Hispanic, single or unmarried mothers received Medicaid. Okay, does that make sense how we go through then? All right, now this is what I would consider a very complex frequency table because there's multiple layers going around. But this is how you would read it. And so when you're looking at a table, some sort of distribution, and it's providing you a descriptive statistic, that's how you need to take it down. So first, where did they get the study from? This one, it's written in the margin. Oftentimes it would be in the text above. Make sure to then look at the title of your page because it most often will tell you what is the unit of measurement for all the data you have below. And then take a look to see what it is that they're actually comparing. So right here in the title, it's telling us Mexican immigrant versus US born. So you're like, okay, so I've got a clue that's what's going on. And I see these here, but then look at all these subdivisions, right? And this is our control group. This is the total US born population. That's kind of what we're comparing everything against. I think that's what these authors are trying to make a point to. So this table, and actually, I think this table is skewed. This prenatal care in first 3 months should have been scooted over here. And then Mexican immigrant is 79, Mexican American 72, because this number is just hanging out. but that's the group that we're comparing everybody else to. That's what the authors would try to make a case for. Okay. All right. This is the same thing, but this is in what is called APA format. How many of you guys are covering APA format in other classes? No? Uh-oh. No one is talking about APA in any of your classes?
I had a whole class on it.
You did, Hasher? Okay, what class was it? Was it at Aquinas?
Yeah, it was, sorry, I don't know the exact name, but it was like a psychology class, but it's all about research in psychology. And we focused very heavily on APA, like we had to learn the ins and outs of it.
Wait, you took research methods already?
No, it was I don't sorry, I would pull up my thing, my
No,
schedule.
it's okay.
It
No,
was-
no, no,
yeah,
it's fine.
It was
No.
like I think it's called Thinking and Writing in Psychology.
Ah, okay. So I could see that totally being all about APA. But no other classes having you guys focus on APA?
Mm-mm.
No? Okay, I'm seeing people. I want to make sure I'm catching all the chats here. You did last semester, Liz. Okay. So, okay. For this class, you don't need to worry about APA at all. So whatever you learned or don't know about, no stress. That's not what the goal of this class is. But as you move through and get into higher level psych or social science classes, APA is the format they usually want. So in terms of in-text citation references, and this isn't the way you would present data in APA as a table. So notice there's no vertical lines between each of the columns. The spacing is all the same. The asterisks show what's significant. Anyway, this is APA. So this table is easier to understand to me because at least everything is lining up. And you can see how the way they've highlighted US born up here, then you know that's one category. Here's your comparative sample. And then here's the additional information. Again, just straight from the other article. Okay, so this is how we present frequency information, whether it's as a percentage or an actual tally and count. That's what that looks like. Intro to life, okay. Now let's, why isn't this working? There we go. Now there's another way that we could visualize data, and that's through a pie chart. Now, how many of you guys have seen pie charts in the past? Right? So many times. You will see something like this, right? Like, okay, I'm making stuff up here. And then, I don't know, socialize. Oh boy, I don't even know why I felt the need to show you this. This is so bad. What is the life of a college student, right? So if the pie encompasses the total number of hours that's in a day, this proportion is sleep, then you can say eat, study, and socialize. I picked random categories, right? That would be a pie chart that would show the whole is an entire day and the division of different activities per day. Hint, hint, this will be on a quiz and exam in the future. Not my disgusting drawing, but understanding pie charts. Okay, so a pie chart is a graph that shows the differences in frequencies or percentages among categories, but the categories displayed are segments of a circle or like a pizza pie whose pieces add up to 100% of the total frequencies. So again, when you have a pie chart, it shows your whole, and then each little sliver represents a portion of that, usually a percentage. All right, so it could look something like this. So this is the 5-year estimates of the US population of 65 years and over by race. Okay, so how many people are age 65 or older, right, that are in the elderly population? And how is that divided up by race? Now, I want you guys to take a look at that and tell me how easy or not easy, like, what are you noticing? What do you see? as I beg for more water. Derek? So what do you guys see?
I mean, it's, I'm not sure if like anyone else really had it, but like at first I couldn't really like tell the difference between the black alone and the white alone in the little box down there. They almost kind of looked like the same color until I actually looked at the chart. And then they're like, the numbers are all kind of like close together, like jumbled up.
Okay, so Aaron, you nailed it right on the head. So this is not an example of a good pie chart. There's several things that are going on. One, the colors are not different enough from one another that visually as a reader, right? Because whenever you have a chart, you are speaking to your audience and trying to convey a message. What is the message that's being conveyed here? It's a little hard to tell. Short that 84.5 is large, but I am even struggling to figure out which category is 84.5. Is that American Indian alone? White alone? That's hard to tell, right? So this is a faulty graph that is not showing the percentages effectively. Thank you. Okay. Now, let's see if this makes it a smidge better. What do you think? Is this easier? Same?
Easier.
Easier? In what way?
I can like differentiate. Well, there's less options because the white alone and the black alone and then the American Indian alone were like so similar that I couldn't even tell what I was looking at. But this way it's a little bit easier to differentiate.
Yes. Okay, so we did here some combining, right? So remember earlier when I said you're going to group things to make it easier in a frequency table? And I said, be careful because you don't want to make it so simplistic that you lose nuance, right? Now, we lost quite a bit of nuance here, right? Because we went from 7 categories to 4. Now, inherently in doing that, I need to ask myself, by creating these new categories, I'm really saying white alone, black alone, other, or 2 or more race. If I'm combining here this 2 or more race, is that going to be significant? Like, or the people that are combined or exemplified through that category, are they the same or are they inherently different? Because as soon as I'm clumping, I'm diluting any potential difference. Now, in this instance, I would say this is okay to do because it is such a small number. If I look back over here, I'm looking at like 0.1%, 0.5%. Those are so tiny. But if I'm clumping them together, now this is a little bit more simple, right? It's a little easier to see. How do we feel about this one? A little clearer? I'm going to assume that's a yes. Okay, thank you, Grace. All right, so that's a pie chart. Oh, the other thing I want to note is that the way the chart was drawn with some of the parts kind of sticking out, that's another way that researchers can do to make it a little bit more obvious as to what the percentages are. You are not expected to do that. If I ask you to create a pie chart, my expectation, you'll just do one circle and then subdivide the inside. This is not an art class, so we don't need to worry about that. Okay, what is a bar graph? So a bar graph is one that shows the differences in frequencies or percentages among categories of a nominal or ordinal variable. So again, the categories are displayed as rectangles. They all are of equal width with their height proportional to the frequency or percentage of that category. Bar graphs are the most common ones that you'll see. You've probably seen 100 of them. Each bar is separated because they represent a separate category and they're not, we'll talk about a histogram in a minute. Histograms touch each other because it's a continuous value. And so this may be 0 to 4, and then this is 5 to 9. So those actually do need to touch. But this would be like the number of students in this class who are freshmen, are like first year in college versus second year, third year, fourth year. They don't need to touch each other because it's not a continuous variable. It's separate categories, right? Okay, so here's what it looks like. So this would be the marital status of US elderly. So again, this is from a study, age 65 and older. I am displaying information. Now I could have put this in a chart, right? I could have said that there's 54% of our respondents claim they were married, 28% widowed, 11% divorced. But this then shows it more visually as a graph, okay? So what can we see from this?
The majority of people are married, elderly people.
Yep, you're absolutely correct. So that would be a very good conclusion from this graph. So the majority of individuals who answered this survey, age 65 and older, the majority were married. Coming next was widowed, which means they had also been married, but their spouse had passed. Okay. So here's another way to do it. Now I'm looking at the same exact data, but I split it. So we went from this with the vertical bars to this, I'm making it horizontal. I could make it vertical too, it doesn't really matter, but I'm splitting the information that I get between men and women to see if there's anything more that comes out of this. So what conclusion might you make based on this graph?
That more men are married.
Okay. What do we think about that?
I'm trying to make sense of it, but I don't. Could it be that they're like gay? I don't know.
Oh, my brain didn't even go there, but yeah, that's certainly a hypothesis. Now, the one that I was like, ooh, was this one, widowed. What do you notice about this category?
Well, I mean, men do tend to die younger than women do, so that makes sense.
So then this tracks, right? So you have almost a twofold. So I'm going to eyeball it here. I would say that there's maybe 18% of men who are widowed to about 40% of women who are widowed. So out of that group, right, who said they were 40% of women said they were widowed. That's almost equal to the number of them that said they were married. Okay. So that would certainly support what we know about age span between men and women, that women tend to live longer. And so therefore they're widowed at a faster rate. But yeah, the married piece, I'm always like, huh, I did this last semester too. I was like, what's that about? What's going on here? More men are married. Is it possibly that because women have a greater rate of being widowed, that then they partner up and don't remarry? I don't know. Any hypothesis works here. It's just how it goes. All right, why isn't this working? Here we go. All right, so this is another way to represent data. You can take a look at a statistical map. Now, I love these. Honestly, I probably shouldn't say this, especially while I'm recorded, but you see these kinds of maps so often, these regional maps with like, who says pop versus soda? Have you guys seen those on Facebook? Or who says Coke, right? Like it's the three, and then you see like areas that are warmer. You'll see this around election time, and you'll see different districts and which way they're polling, whether they're Republican or Democrat. So a statistical map is taking frequency data across the entire United States, usually by district or county, and then we'll create some sort of labeling system. So this specific one is the unemployment rate by county between March 2009 and February 2010. And then you can see here the rates of unemployment. So 1.9 or below is this light yellow, kind of almost white. Can you guys spot any area on this map that actually has this color? Because I am not.
I can't tell if there's like a little divot in Louisiana there.
Aaron, this is gonna get embarrassing. I'm like, where is Louisiana on this map? Like over here? No? Here? Here.
Yeah.
Okay,
Yeah.
here. That's a lake. I don't know. Okay. So, and then you see 2% to 2.9. There's definitely several regions right here, all the way up to 10% or higher, which I don't know. Woohoo, Michigan. Check us out. We were struggling. And then this purpley color is 7 to 9.9%. So again, what is the takeaway? If you're glancing at that map and you're looking for a job, where should you move to?
The green belt.
The green belt? I don't even know what that means. What is the green belt?
All the farmland.
The farmland. Okay, because what is that? Is that North Dakota, South Dakota,
Maybe Kansas or something.
Omaha, Kansas? You guys, okay, did I mention that I'm Canadian? This is the reason why I'm not good at geography of the US. We're gonna stick with that's the reason why, and not that I've not spent a whole lot of time on it. Okay, but anyway, so just glancing at it, right? If someone asked you what is the unemployment rate of the entire country, right? You would get one value. Then maybe if they said, what's the unemployment rate of each region, the Northeast, Southeast, the Midwest, you could divide it up that way. But how much richer is this table? You just get to see so much more about what is going on regionally by county. So we often use these maps, again, like I said, for voting patterns, crime rates, population distribution. This is another big one where you see like the areas that are heavily populated by metropolis. So that is another way to communicate data that makes it easier to grasp and understand than if you were just putting it in a large table, right? The message wouldn't be conveyed as nicely. Okay, and then finally, there's the histogram, which is what I was talking about just a minute ago. It's a graph that shows the difference in frequency or percentages among categories of interval ratio variables. So again, we're looking at a variable that has an actual number, and that is why the histogram bars are right next to each other, because then each category comes right up to the next one. So they're contiguous, they're touching with width that are proportional to the width of the category, and height that's proportional to the frequency or percentage of that category. So here's what it might look like. If I am looking at the age at death, again, your textbook is very uplifting. Age at death, I can look from age 20 all the way to a little over 100 and how frequently they occur. So what is the takeaway of this histogram? What do we think? Just glancing at this, what are you learning from it?
That majority of the people die between 60 and 80.
Okay, so I can take a look at these bands here between 60 and 80, and those seem to be the highest one compared to everybody else. Okay. Aaron, if you're talking, I think you're muted. We can't hear you.
Oh no, I was just talking to myself. Sorry.
Oh, okay.
Yeah.
Okay, so you're absolutely right. So Lainey, talking about 60 to 80, that is definitely the highest proportion section. If I look at 20 to 40, that's fairly low, but actually 80 to 100 is fairly low. So if someone said, are you more likely to die between the ages of 20 to 40 versus 80 to 100, the answer would probably yes. But what is the reason behind that? Why is there a greater number of deaths between 20 and 40 than 80 to 100?
There's a larger population. I don't know.
You got it.
Okay.
fewer people make it to 80, right? So this is again, how old you were when you passed away. So if you didn't make it to 80, this is not a cumulative percentage, right? Or cumulative frequency. This is just how old were you when you passed? There are fewer people here. Now, I want to draw your attention to the statistics here. Here's important pieces. The mean is the average age that people passed away. This table tells us that in this sample of 2,291 participant, the average age at time of death was 60.23 years old, okay? So if I go back to my histogram, that would be like right here. That would be my mean. And the reason why is I've taken all 2291 entries, added up all of their ages and divided by 2291. That gave me an average of 60.23. So that is the average spot, okay? We can talk about skew, but I think I'm just gonna leave that be for now because we're not there yet. Okay. So histograms are going to be the bulk of where we spend our time because in statistics, we use more often interval ratio variables than nominal or ordinal variables. We're interested in getting numbers, and inherently by getting numbers, those are continuous variable, they're interval ratio. So there's several types of frequency distribution that are observed when we draw out a histogram. This is what would be considered a unimodal distribution. Another word for it would be a normal curve or a normal distribution. In other words, a normal distribution would say that the highest point is at the midpoint and it's mostly symmetrical around the mean, okay? So when somebody talks to you about an exam and they're like, oh, what'd you get on the exam, right? And you're like, oh, I got an 82, fantastic. And they may ask you, well, what was the average or what was the mean? By the way, give me a reality check. Is anyone having these conversations or am I picking a super random example that you're like, that is not relatable? That's what I did in my undergrad class. Okay. Anyway, back when dinosaurs roamed the earth, I would ask my friends, what'd you get on your exam, right? And then we talked about what was the average on the test. And they would say, oh, the average was 74. And I'd be like, oh, I got an 82, 74. I did all right. That's because I figured the average, the highest point right here was that 74. And I got an 82, so I was here. I was above the mean, right? So if everything is normally distributed, right, it's even on either side, that means I fell above average. Now, if I had a really easy professor, I'd be like, ooh, I got a 95. I rocked this exam. Hey, what'd you guys get? Now I'm getting answers. And then the mean would be written, oh, the average is 91. I'm like, oh, okay. Well, that would be a type of distribution that is not normal. It would be a skewed distribution. Here, let me show you. So it looks something like this, right? And if this was like, wow, 90. Oh, you guys, my handwriting is not great. And it would be something like this. Shoot, shoot, right? That is a skewed distribution. That means the highest point was over here, but that was at a very high score, not a normal distribution like this. Okay, so those are two types of distribution. I can also have a bimodal distribution. So notice there's a peak here and there's another peak here. And we'll talk about this. I have several examples of that, like how frequently you go and visit the doctor, right? It might look, actually, it wouldn't look like this. Let me draw that out too. How often do you guys go see the doctor, would you say?
Once a year?
Yeah, if that, right? As an adult, probably not. What about babies? Everyone's muted, so I can't hear you.
Once a month, maybe?
Yeah, so you give birth, just as FYI, you give birth, 3 days after birth, you need to go take them to your pediatrician. then it's 2 weeks, then you got 1 month, 2 month, maybe 3 month, 4 month, then 6 months, a year, right? So a lot. So it would look something like this, right? You go see a doctor a lot when you're young, and then it goes down, it goes down, it goes down. And now you've just hit 40. And now it goes like this, right? Because in old age, you see the doctor more often. This would be considered a bimodal distribution. In other words, there are 2 modes. We'll talk about modes, mean and median, I think next time. That's measures of central tendency. But there's 2 high points. So you see the doctor often when you're an infant before the age of 1. You see the doctor often after the age of 65. Okay, this would be just an example of a bimodal distribution. There are some distributions that they are approximately rectangular. For the sake of this course, this will be very unlikely. This would be a case of never having done something, then doing it a lot, and then keep doing it and not doing it at all. So this may be, one example I had was like attendance or frequency of visitation at a library. So maybe not at all, not at all. You start college, shoop, and now every single day you're going to the library, you finish college, never go again, right? That would be the example of a rectangular distribution. Okay, so the shapes of distribution, continuing with that idea, is they can be symmetrical like this, meaning I can bisect it, cut it in half, and if I were to fold it over, it'd be about the same, right? Symmetrical. Or it can be skewed. Now, these are not grid graphs. Again, this is from your textbook, but this one is a positive skew, meaning it's closer to the left. And this is a negative skew, so it's further over to the right. So again, this would be a class with an easy test where they got higher scores more often than lower scores. And this would be a specifically challenging test where the bulk of the class maybe got a D and very few people got B's and A's. Simple example. This will not happen in this class. We'll be right over here, maybe right in between, or not in between, we'll be over here. Hey, hello. Okay, so we've talked about the shape, right? Can it be single modal, bimodal, rectangle? Is there going to be skew or normal distribution? We can also talk about the kurtosis of a distribution. That is how much variation there is within your sample. Or you could call it how much deviation from the normal curve is there in terms of the scores represented. So if this is my normal distribution, this is my mean, right? And it's perfectly distributed. If I fold it in half, it's the same thing. This assumes a deviation, and we'll talk about that later this semester, but if I get, and I need to see your faces again, because I want to know if people are super confused. If out of a test, most people scored a 75 and the highest score was an 81 and the lowest score was a 60, right? The scores are all really clumped together. There's not a lot at the tails. That would look more like this. So there's hardly any of these scores, and then we go straight up versus these, right? Now, if I had a class where there's no scores at 0, right? And then I start at 50, 51, 52, 53, 54, 55, 60, all the way down to 87, and then nothing at the tail, okay? See how the variance or how wide of a range of scores you have will also impact your graph, how normally distributed it ends up being. Okay. All right. So this is just a bunch of examples we'll talk about. This is the number of people in a toddler's area marked by age. So when you've got an infant, or this is, if we're going to go toddler, maybe this is age 2, you've got lots of kids that are hanging out with them. And as they get older, they do more singular play. And as they get to age 4.5, 5 years old, they do a lot more pretend play with peers. So it climbs back up. Okay. I think that's a good example, but I don't think it's as good as my visits to the doctor's office. I think that exemplifies that a little bit better. Okay, but just another example of how you can have a bimodal distribution. Okay, floor and ceiling effects. That is something else you can have when you're doing a graphical representation of numbers. So this is number of families and number of children. So you see, this is number of children per families and how many families have that number of kids. So you could see here, you have one family with 6 kids, and you have multiple families that have no children. There is, you see how this graph starts really high, right? There's no, it doesn't go slow up. That's because there's a floor effect. You can't have negative number of children. That's not a possibility. So you start at 0, that's the absolute lowest you can have, and you can have a lot at that point. So that's why you end up having this kind of odd setup. A ceiling effect is, again, I cannot get more than 100% of the correct answers. So it ends right there. It's possible that multiple students had 100, so that's why it ends really tall, but I can't go beyond that. That's a ceiling effect. Of course, many of you are like, what about extra credit, right? But for this particular example, there's none. Okay, how are we doing? This class ends at what time? Give me a reality. It doesn't end at 8, it ends at 9, right? Okay. Whoa. Oh, y'all look very excited. You're like, oh, the pain. We'll go for a little bit longer because we can do this. All right. A line graph, that's another way you can represent data. It shows the differences in frequencies or percentages among categories, now again, of interval ratio. So we've got histogram and line graph, both of them for interval ratio. The points then on your graph represent the frequency of each category, and they are placed above the midpoint of the category, and they're then joined by a straight line. So they're made to connect via the straight line. So here it is. So this is the population in Japan, age 65 and over, between 2010 and 2014. So you can see that the lines are delineated by either dotted or solid line. And so you can see here, they had a point. So for in 2010, it looks like maybe a little over 8 million people fell in the 65 to 69 age category. And then you look at 70 to 74, maybe it was, what is that? Like 7 million. I'm kind of eyeballing it here. So that would have been another dot. And you can see they connected it with a line. So you see something more continuous. So what would be the take home message from this graph? What do we think?
The number of elderly was greater in 2014 than 2010.
Yep. So we see there's a difference there. In 2014, the line is above 2010. Yep, absolutely. Also, perhaps this is a normal thing you would see in any country, but you have a greater number that are in the larger age band than the lowest age band. Although here in 2014, there's kind of a flattening, almost like people are aging a little bit longer. So again, I want you guys to see that with these graphs, so a researcher did this study, right? And they're showing us this graph. Without having read the study, we're able to come up with some hypothesis as to what they're trying to communicate to us. We may be right, we may be wrong, but if they have decided to present data this way, and we come up with what is a faulty assumption or faulty conclusion based on their data, that tells me that either their result or their conclusion is faulty, or they have picked the incorrect way of depicting their data graphically, right? So we should all give it a shot and try to see, like, what is this telling me? Why do I care about this? Well, the why do I care? You will ask yourself that question a lot with the textbook because they come up with weird examples. But what are they trying to tell me? What is the message here? And then we'll talk about, oftentimes in this class, this is the result. This is the discussion. This is what seems to be happening. And does that line up with your hypothesis? A lot of what we do in this class. So yeah. Okay. Another way. You're like, how many ways is she going to talk about sharing data? I just have a couple more. A time series chart is a graph that's displaying changes in variables at different points in time. Okay. So when you're doing longitudinal data, meaning you are continuing to graph and check and measure a specific data point over the course of time, you are going to be graphing that in a different way because you need to highlight the different spots in time to see if there's any trends that's happening. So it shows time measured in units, such as years or months, depending on how you're doing it, on the horizontal axis, and the frequencies in either percentages or rates, that's going to be on the vertical axis. And it looks something like this. So this is the percentage of the total population age 65 and above for selected world regions. So we can see in 2010, and then what is happening here? What are we noticing about time?
As time goes on, so does the percentage of the population 6 years and above, 65
Okay.
years and above?
Yes. So very good, Hasher. So how did they get data from 2030 and 2050? Just curious. I can see all of you are like, I hadn't quite put that
Is
together.
it just a projection?
It is a projection. No, the authors traveled in time. They had that unique ability to do that, but they only grasped this information. They could not have forecasted some of the nonsense we've just been going through as a country. Just kidding. Let's not go there. But yes, those are projections. So if you're looking at rates, and honestly, we can kind of figure this out, right? Because if we're trying to figure out how much of the population is going to be 65 years or older, and I know how many people are 40 today, then I can kind of figure out how many people are going to be 65 in 9 years. And then how many people are going to be 65 in 29 years, right? Provided they don't die in between, accidental cause or whatever. So I can project. So what is the message that we are reading from this? And Hasher was on the right path there.
People are living longer. Don't know.
Okay. We have an increasing rate of older adults living through, right? Projected through, which implies what? So oftentimes these graphs are shown to see like, hey, we have an aging population. We have more and more people that are in the retired and elderly category. What does that say possibly about the number of people, like the younger people? What does that mean in terms of the economy? What does that mean in terms of healthcare? So there's a lot of global implications at looking at an aging population. Now, this particular graph is giving you a projection, but it's also splitting it by different regions. What do you notice about the different regions?
Well, for besides golly, I can't tell which one that is. The second to bottom one in North America, for the other three, they all kind of just like indent and go upwards. It looks like just a little bit more. While then the other two are just kind of, I don't want to say flatlining, but that's what they look closer to.
Okay, so it looks like Africa is being pretty steady in terms of their rate of 65 and years and older, right? The bottom line, that's almost flatlining. So they're pretty consistent. But if you look at Europe, and I think that is North America, they're definitely climbing in their rates of the elderly. Is that what you were mentioning, Aaron? I'm sure I got what you're saying.
Yeah, like I was trying to talk about how, unlike the different cultures, how like each one kind of has its own uniqueness.
Yep, totally. Okay. Okay, so that's another way you can show a time series. It's divided by time. Now, graphs not only are helpful at giving us a message very quickly, they are also quick to deceive us. How many of you have gotten hit by either a graph, you know, in a commercial or print media, and you've been like, what is this trying to tell me? And you've kind of given pause to it. Has anybody done that where you're like, that thing is rigged? No, all statistical data has been squeaky clean for all of you, or maybe you've just not noticed it. Okay, let me tell you the story of when I was forced into a multi-level marketing gathering. Maybe it was my own fault. I was invited over to an acquaintance of mine. She's like, come on over. We're going to have some snacks. I want you to meet some people. And I show up and this lady has all of her, oh gosh, and I forget the name of the company now. Pure Haven. I feel like that's not right. It's like a natural products thing. But it was obviously like she was here with all of her accoutrement, like all the lotions and the things to sell. And I was like, this is not what I thought this evening was going to be like. I've been duped. And she had her little, you know, stand. She's showing data. And again, I mean, no judgment. If you do the Norwex, whatever thing, totally fine. Just as long as people know that's what they're getting into. And I did not. And she's turning over all these slides about the number of chemicals that we have in our bodies. And she's like, here, because of the number of chemicals in our beauty products, right? They've been increasing. There's chemicals in everything. Look at this rate of increase over time with fertility issue, with cancers, rates of autism. I mean, it was everything was like included, like had skyrocketed. So it was literally a chart, if you can imagine it, going straight up in time. And so it was a time serial graph. And over time, it also showed the increase in chemicals and what we would put in our beauty products like lotions and all that. Now, I love stats and I love research and I geek out on that stuff. What might be one of the thoughts? Well, no, you don't need to know what my thoughts were, but like, what would you wonder when you're looking at a graph like that, that seems to be very much saying chemicals are then leading to increase in cancer, fertility issue, autism, all of that?
Like, what is connecting the makeup to all of that? I guess.
1,000%. Yeah. Okay. What is the relationship between these two things? Because you could take out the chemical in makeup and introduce a bunch of different variables that I think would also support that. So, cell phone ownership. Do you know what? In 1980s, people didn't have cell phones. And now everyone has a cell phone. Ergo, fertility issues are due to cell phones, right? Okay. Let's introduce something else. Yes, Hannah, you're absolutely right. Maybe brightly colored cars, because car manufacturers have recognized that they can have a variability of car colors to appeal to a larger range of consumer, right? And so now you'll see a green car, a pink car, a yellow car. The yellow bugs, definitely see that. And back in the 70s, that wasn't a thing. So I think it's car colors. What about computers? What about brands of Skechers was not around in the 70s. There's way more Skechers around. That's probably, do you see what I mean? There's a problem here. So you can insert just about anything as being causal, and we'll talk about that in research methods, as causing something else. And you can show a graph that unless you pause and think about it, you might go, oh, I guess I never thought about that, and it must be true, right? So I encourage all of you to show great critical thinking skills, because sadly, the world we live in will utilize graphs and charts, and well, charts are a little harder to manipulate, but graphs especially, to show something that isn't actually there. Okay, let's take a look at some greater examples that I have of this distortion. So what are we including when we say graphical distortion, and how can we recognize them? So sometimes it's not using equal interval sizes, which all of a sudden seems like you've got one group that's way taller than the rest. Or sometimes you exaggerate proportions. So by shrinking or lengthening your vertical axis, you can make it seem like there's a much larger difference than in fact there is. If you are not including error bars, you're not showing the true picture, because there's always a certain rate of error in our measurement. No stats is perfect. All right, so let me show you an example, okay? So this is a frequency distribution that is showing unequal interval size. So we've got 79 to 70 at 9 and 57 to 50 at 7, okay? Do we see here? Do you guys notice the difference here? Okay, so this bar shows that they're being paid the commission to travel agents, and 76 is paid 50, and then in 77 is 57. But then look here. That's a $9 difference versus $7 difference, and the graphs don't look the same at all. And then here's another $9 difference. That doesn't look the same here, okay? So when they're not all right next to each other, it becomes very challenging to then see the difference between the two, okay? You're just gonna look at it and not look at the numbers, right? That's what most people would do. They'll go, oh, whoa, look at this. And yeah, wow, this one's big. Oh, but these are really not that big of a deal, when really it's about the same, okay? Here's another one. So this is a distortion because axis can be stretched or shrunk to create a certain result, okay? This is the percentage of female that are represented in the national parliament in 2015 for each of these countries. Okay, now what do we think? Pretty different, pretty similar? I mean, a little bit different, right? It seems like Rwanda is just kicking tush here in terms of female representation. And then this is kind of flatter, right? Okay, now I'm going to change the y-axis and notice if you see anything different. Right? Doesn't that seem like a stark difference? All I did here, if you go back, these are intervals by 10. Now these are intervals by 5, and they don't start at 0. Okay, so I've shrunk it to create a certain desired result. Okay. Again, this is not starting at 0 creates a problem. So if my vertical axis is starting at 150,000, I can see a lot more variability between years. But if I start at 0, I'm pointing, you can't see my screen. This is why I've got this, right? If I start at 0, you see that these guys are actually, they're pretty similar. But this makes it seem like, whoa, what's happened here? Okay, same exact information. I just distorted it because of the graph and how I displayed my results. Okay, this is, again, a histogram that shows the stress rating that's distorted from the standard from 1 to 1.5. Okay, excuse me. Ooh, yawning too. All right, so do we see the difference here in just, again, how it's shown how much that's distress? That's just, again, looking quite a bit different. And that's just, again, by stretching it out, making the table bigger, right? From this to that. This shows like, whoa, this is much higher. All right, same with this. Now notice my vertical axis from 9100 to 9800. I see quite a bit of variability. Now let's see if I change my vertical axis. Same exact result. Okay, but if you saw this, you'd go, there's no difference. These are all the same. If you saw this, you'd be like, well, yeah, group E is a lot higher than group A. Okay, so whenever you see any graphs, always go back to your vertical axis. What is the measurement? Are they actually that different? And more specifically, if you're reading a research article, go into the text and see if they state that there's a statistical difference. Now, it is possible, I'm not saying it's not, it is possible that in fact, this group A is statistically different than group E because they have a large enough sample size and it shows a statistical difference. But chances are, if your score is, I don't know, I'm eyeballing it again, but 9350 versus 9750 out of that large of a scale, that may not be significant. Okay, here it is. IQ is a function of gender. This is saying males are smarter than females. So obviously it's not true, not right? Right? Okay. Now, there's no error that's noted on here. If I switch it to this, what did I do different here? What changed between the two graphs?
You gave each like a little bit of wiggle room just in case there's some people that have higher IQs.
Okay, so Hannah, spot on. I added the whiskers, which allows for standard error. Yep. What is something else that's different between these two?
The Y.
The y-axis. So Hannah W, say what you mean by that.
So you like lowered the numbers and it's actually like not that big of a difference than they make it look out to be.
Yes. So average IQ, I don't know if you guys know, average 100. This starts at 100, right? Okay. So that's not the natural, and IQ has a natural 0. I mean, I don't know that you can get a 0, but you can get a much lower score. So this here is highlighting the difference. Again, maybe it is statistically significant in their particular study. Hard to know. But this is certainly trying to tell you something. This is telling you guys are way smarter than gals. But when you put it on a chart that actually has a natural 0 that goes up to your highest point, you see the difference is actually not all that significant, right? And even on this, if you pause and think, that would be what? 105 to 114. So we're dealing with 9 points. Not giant. Okay. Again, distortion happens all the time. So not starting at 0 can have a huge effect, right? If you start at 0, you see that this is not really changing a whole lot. All of a sudden, you cut to 3650. Now you're like, whoa, look at this massive dip. Now it's important to note, sometimes we want to highlight this. We want to go like, hey, what happened here? And had we not paid attention, we might have just seen a blip, right? And not paid attention at all. So I'm not disputing that sometimes it's important to look at the small detail. But when you're communicating your entire research to your audience, do not distort it to make it seem like there's a bigger difference, especially if there is no statistical significance, okay? Again, you see here data from 1970 all the way to 2005. If you change your rate, so this is already just a factor of 5, they changed it here to 0.05. I think that's what it is. 0.05. So whatever, I don't even know what this measurement is. I'm not sure that we need to go that low. It seems like a stretch. Okay. So in stats, we will use all of these. They're particularly suitable when we're trying to make comparison among groups. So bar charts, again, you can have male, female. Line graph, you can have multiple regions or countries. Time series charts, you're comparing different time zones. Histograms, though, is not a good measure amongst multiple groups. It's usually its own group and what's the distribution with it. Okay. Why do we use charts and graphs? Well, because it's a little easier to communicate stats that way, okay? So you can look at a table more easily. You can see additional relationships sometimes that pop up. Again, if somebody had just given you data on the rates of marital status among 65 and older in just a table, you might not have spotted right away that widowed had such a large difference between men and women. So it's just a little easier. But you also have to be careful as to the pitfalls, right? You need to use them accurately. And okay, I have seen this time and time again, and this is why I included here. I'll have students go, can you make me a chart just for the exam? Like create a chart. And I've had students text me like, I can't, I'm not even done. I don't know. The chart's taking me forever. And then I get this product that should be in a graphic design class because they highlighted colors and shading and stars. And so you can get caught in the weeds in formatting. Don't do that. Just try to do it as simply as possible, especially for this class. I'm not looking at a PA to get you down. Okay, so what do you gain? You gain your reader's attention. It's very quick to look at it, see what is it that's being communicated, rather than using a narrative. You know, there's just so much you can write in the research study that people are like, oh, I'm done reading. Again, some people in a table format might go, I have no idea what I'm looking at. What is the variable? But if you put a graph, that's much easier for them to grasp. And then oftentimes you can look at the big picture. It allows you to kind of take a step back and go, what is it we're looking at? Big picture, step away forest from the trees. So that's why charts and graphs are quite useful. Okay, key terms. Make sure you review these. You will see these again in quizzes and exams. You will need to know how to create a frequency table. This is when, again, we will practice it for our lab next week. We will practice having people, and I can stop sharing here so I can see your faces. We will practice creating a frequency table, and we will practice putting that all into play and how to use a pivot table. If you do not have access to Excel, please do let me know. You can do most of what we're going to do in this class using either Excel, Google Sheets works really well, or if you have a Mac, using Numbers will work. So next week, we're going to be working through a lab together, and I'll prep you on how to do it, and then you'll be able to complete it at home and turn it in by next week. I just did a lot of talking. Any questions? How can I be helpful? Is this making sense? Sorta, kind of, okay, all right. Go digest this info. Let me know if you have any questions that bubble up. Make sure you respond to the stats discussion. You have to respond to at least 2 colleagues by the end of tonight. So if you've not done that, make sure you get on that. Otherwise, then I'll plan on seeing you all next week. All right, so good to see you guys. You got to tell your roommates, Erin, I expect to dance every class now, so they better start our class well. It's your participation score, so it depends how much you care about that. I'm just teasing.
They would be happy to oblige.
Okay. All right, you guys have a great night, and we'll see you next week.
Have a great night.
A good night.
Have a good night.